Welcome to CS 109 Lab 11. I think this is the last lab.
There may be one more, but it won't be done in class.
Yes.
It won't be done in section.
Right.
This is the last lab to be done.
So this is the last lab that we're going to cover in section. So we're going to talk about a few things. So I just want to talk about projects and then show you a project that we thought was really great. It's not a project for this course. It's actually like a professional project, but we liked it so much that we wanted to talk about it. So that's the example project. I'm going to talk first about project guidelines. So there's on the website there's a projects tab. If you haven't read it in a while, go ahead and start looking at it now, because you might be finishing up the last homework, but there's other projects are coming up, so we want you to start thinking about that already. And then in the middle of the project, they actually use elastic net regularization. So it's sort of an extension of Lasso, and so we're gonna show you that. I don't think we've covered it yet, so I still wanted you all to learn something semi-major in this lab. So first, we want to talk about projects. So you're going to be working in groups, and so I just wanted to give a few recommendations. Being in constant communication when you're working in groups is really important. So we use Slack actually for the TFs, and it's helped a lot for exchanging files and keeping in contact. So I'd recommend that. And of course, using Git and GitHub for the project is going to make things a lot smoother near the end when you have to actually share it with everyone and make it public. Okay, so I'm just going to sort of hover over here to the projects. There's a gigantic they talk about a lot of stuff here. I'm just going to pluck out the things that I want to talk about today. So first, it's really important when you start developing your project ideas, your proposal should be in, but you'll notice that your project will evolve through time, especially when you're working with the group. But it's always important to keep in mind what the purpose of the project is and what's the goal. We want you to and this is straight from that page, is we want you to go through the complete data science process. We've talked about this a lot. And how we want you to go through it is we want you to acquire data, design visualizations, run statistical analysis, and communicate the results. And one of the things that I really like about this next project that I'm going to talk to you about is the communication of results. I think they did a really good job at that. And so we'll talk about that as we go on. So the milestones, the proposal is due today as we're taping this. So if you're watching this later, 2 or 3 days ago, but starting Friday or maybe a few days after that, you'll be assigned to your TF as an advisor, and they'll contact you about meeting with them. And it's important that the entire team meets with the TF. Because then everyone will have input and everyone will get to know each other, and that's really important. Okay, so one of the major parts for this class, for this project, is the IPython process notebook. And I thought it was so important that I just completely copied this out. I did put a little bar here to mean that it's referenced out. So the IPython process notebook is supposed to sort of take us through your journey of this project. So initially you have a motivation and an overview of the project, what you think is going to happen, or what the goals are for the project, and also related work, initial questions. So a lot of this is actually can be expanded on from your proposal. And it's really important that you have all these things there so that when we're reading your project, we know sort of what the journey of the project was for you and your group. So I'll get to the presentation on this next section. But go ahead and read that, and I think it's hopefully really clear. If you have any questions about it, do ask your TAs when you meet with them. Okay, so there are several final products from this project that I wanted to go over. First is the code. The code, so the IPython Process Notebook should contain the majority of your analyses. But just remember, throughout the entire semester, we've been grading on clean code, commented code, code that runs, all of these things. So just keep all that in mind when you're submitting any code for this project. We're also asking you to make a public website. So GitHub pages, so you can match this up with your repository, and it's really nice. So go ahead and look that up if you don't know about that yet. But the website has to be public, and we'll talk a bit more about what the web page might look like and what's important. Well, I mean, so I have it here actually. So we want the website. The website is public, so anyone can read this. What that means is that anyone should be able to read this, and it'll summarize your main results and tell sort of the story of the project. And but again, anyone should be able to read this, and there you'll provide links to the GitHub to your GitHub repo and to your process notebook that we talked about earlier. And then the final thing is a 2-minute presentation. So this can be a screencast, and we really do mean 2 minutes because there are so many projects that we want it, and it's really, I think, good practice to be able to condense a project down to its bare essentials, and that definitely can be done in 2 minutes. And then you're going to upload it on YouTube again, so that people can see it publicly, and also embed it onto your web page. So in the 2-minute presentation, you want to focus on the main contributions rather than technical details. So we don't want to. Anyone should be able to watch this and get a gist of what's going on. The process notebooks are for us so that we know exactly what you did, but anyone seeing this online shouldn't need to know all the technical details. And then one of the things you want to point out, or some of the things you want to point out, are what did you feel? What do you feel is the best part of your project? What insights did you gain? What is the single most important thing you would like your audience to take away? And then really importantly, when you embed the video, make sure that's one of the first things that people see, so that they watch the video and then they can read the rest of your web page. Okay, so then finally at the end, there will be a peer assessment. So remember, you're working in groups. It's really important to work well together, especially because in data science, no one really works alone. It's an interdisciplinary field, so you're going to have people from very different backgrounds working together, which makes it really great. But it's important that you prepare and contribute and respect those ideas and are flexible. Okay, so and here's the grading criteria. I'll just have you look at that, but some of these things hopefully will get ironed out, like the project scope. That'll hopefully get ironed out in the next week with your TF. But yeah, so those are the things we're definitely going to be looking for. Okay, so now I want to talk about an example project that we thought had a lot of the types of things that we think would make a great project. But of course, this wasn't done for a CS 109 class, so it's not going to have a lot of things we're asking you for. It doesn't have a video, and it doesn't have an IPython notebook process. They actually did all the analysis in R, so it's not. This is hopefully just meant as an example that you can look at and say, like, okay, so here was the scope of their project. Here's what types of analysis you might do, and things like that. So I linked some articles if you want to read more about this project. But this is done by the city of Chicago. So the city of Chicago has a gigantic, and I'm going to add a link to this if you download it later. I realized I didn't link to. Oh, maybe I did. Yeah. So It's data.cityofchicago.org, and they have a really great open data initiative where they basically all of the departments get together and they release as much information as they publicly can. And so anyway, it's in general, if you're still looking for ideas or still bouncing ideas back and forth within your groups, this might be something that you can go get inspired by. There's a ton of data, and this is just one of them. So let's go look at their webpage. So this is the webpage, and it's built on GitHub pages. So you can see it up here, github.io. So some of the sort of things that I want to point you to, let me zoom out a bit, is, so it's written kind of like in a article style. It's meant for anybody to be able to read, and it has information about the data, where the data comes from, what was the purpose of the project. Their main results are here. So you see basically what they wanted to do, and we'll talk more in detail about exactly what they did, but they wanted to be able to predict what food establishments might have critical violations. So this is things like the temperature of the food was too low, or cleanliness, things like that. So they want to be able to predict which types of which establishments would have that. And using their method, they were able to improve on the number of days to discovery of these critical violations in restaurants in Chicago. And we'll talk about exactly how they arrived at these results. But they have other results here that say like, what kinds of predictors for food inspection outcomes. So what kinds of predictors led to their predictions of critical violations. So they list a bunch here, and there's some interesting ones like nearby burglaries. Apparently, is a very predictive variable, and length of time since last inspection. That's interesting. And some of these make sense. So 3-day average high temperature in the city. So if you're going to be inspected on a hot day, you're more likely to have violations because I don't know why, but it's interesting. And lastly, which we'll find is really important, is the inspector assigned. So each food vendor has an inspector assigned to them, and some of them are harsher than others, and we can see that, and we'll be able to show that. But in general, what I want you to get from this website is that it's very readable. It's meant for anybody to be able to see, and they talk about where they got their data. So here's the data portal for Chicago's data portal. So I'm just going to click on it just so that you can see all the data they have. So they have a ton of data. They have towed vehicles data. They have police station data. Anyway, they have a ton. So if you're still looking for inspiration, go ahead and look at that. And so then they actually talk about how they evaluate their model. So this is my favorite part of their project. Because we've learned how to do prediction. We've said, you can predict a 0 and a 1 using SVMs. You can do logistic regression. You can do trees. You can do all kinds of things. But how they actually validated their model, I want to say that again. How they actually tested their model is they worked very closely with what the intent of the project was, which is how do we schedule visits to food establishments in a way that helps us find these critical violations. So they didn't say our method had really good accuracy. They said we were able to get to these establishments 7 days earlier, and that's really, really important because it's tied together with the overall view of the overall scope of the project. And so these are the kinds of things I want you to keep in mind because we've been talking a lot about using accuracy, using F1 scores, using all of these things to say our model is good, but there are other ways to do it, and this is a really, for me, this is one of the better ways I've seen because it's so closely tied to the project. And then they actually also have a link here, which we're asking you to do, to their GitHub repository. So the GitHub repository, again, all this was written in R. So if you know R, you should check it out. They do some interesting modeling decisions, but it's all here. So it's completely open and viewable by anyone, and you can actually fork it. I have my own fork of it. You can fork it to look at the way they did things and things like that. Okay, so the last thing I want to point you to in here is the report. So if you go into reports, there's a PDF. It's the last one. There's a PDF, and this is their actual report. So they work for the city of Chicago, so they're not exactly students, and some of them work for Allstate. So they wrote a report in the end, sort of detailing all of their exploration and their analysis. They didn't put in all the details that we're asking you to do in your IPython process notebook, but this is relatively close, except that it's in R Markdown and LaTeX. But otherwise, it has a lot of the things that we're asking for in the IPython process notebook, but do stick to the guidelines in the IPython process notebook of the web page of the course web pages, so that because that's what we're going to be grading you on. And so I'm going to talk a bit about the results that they got and the models that they used. Okay, so just to reiterate, so what are some of the questions? So about the web page, I want you to sort of start thinking about this as you read the web page. Say, was the writing directed appropriately? I thought so. Was there enough motivation to get you going on, why they were doing this and why they think it's important? Do they link their sources? That's really important. And so I wrote down what I thought, and actually what I grabbed from, this is just a copy of the goal that they had, so that the results that they give are very much tied to this goal. So their goal was to forecast food establishments that are most likely to have critical violations so that they may be inspected first. All right, so that's the goal. And again, they didn't want to say, I predicted it correctly, yay. They wanted to say, I think this is right. Let's go a bit earlier to inspect this food establishment. So, and of course, their main result, I just plucked it out here, and the data. Okay, so first, again, a lot of this code was done in, or all of their code was done in R. So what I did was I wrote a different IPython notebook, which is the part 2 of this. It's essentially just going through and it's using R magic. So if you ever run into R code that you want to use that someone else already wrote, there's this thing called R magic, which is great, and you should check it out if you're interested. Yeah, that's sort of it. I basically took the data that they had, processed it using their code to get it to a form where we could just run the model, because that's essentially what I want to talk about today. So this is R. So if you recognize it, there's a little arrow thing. It's kind of a quirky R thing. But what's important is that, okay, now we have some data to work with. So let's go ahead and read in the data. So it's actually pretty big, so I'm not going to read it in right now. But there's 97,000 inspections. This is data collected, I think, from, let's see if it has the date. Yeah, 2010 to 2014. So there's 97,000 inspections done in 4 years. So it's a lot. And one of the things that they do to motivate wanting to schedule this appropriately is that they only have like 36 inspectors. They only have 36 inspectors. So to do 97,000 inspections, so you really want to get this right. You want to be able to get into the restaurants that you think might have violations earlier, just to sort of save, to help prevent outbreaks of things, because that's their job. And so here's what the data looks like. There's an inspection ID. There's the name of the place. What kind of place is it? What kind of inspection type it is. So that this one, for example, was a complaint. So someone actually called and complained about this restaurant, so they went and checked it out. This is a canvas. Canvases are just regularly scheduled inspections. Different types of restaurants have different schedules of regular inspection, once every 1 year or twice a year or every 2 years, things like that. Okay, so first thing we're going to do is focus in on the 2014 data. So I just read this in here. So here's what the 2014 data looks like. There were 20,000 inspections in 2014. Again, this is just me looking at it. Okay, so what I want to do is in 2014 count the number of inspections. So this is just data exploration. I just want to look at what types of inspections were they. The majority of them were just regular canvases. They're just regularly scheduled visits. There were complaints. There were about 2,200 complaints. And so this is just sort of to get an idea of what the data might look like. And here is, so one of the things that's really important is this risk label. So the risk label, essentially, what it is if it's high risk, it just means that it's not like a risky business. It's just labeled as a high risk business in that they handle food, they handle hot food, so they just have a higher risk of something going wrong. So they're inspected much more often. They're inspected, I think, twice a year. I forget it exactly. So I forget what medium is, but low is places that have packaged cold food, like grocery stores and things like that. So they're much less risk to have issues. So again, the goal of the model, the goal of the project was to be able to schedule the visits by these inspectors to the different food vendors. But the goal of the model is slightly different, right? So the model can only predict. It can't. You have to decide how to use the predictions. But the purpose of the model is to predict whether or not a particular establishment is going to have at least one critical violation. And if we can predict it, and the probability of that happening is very high, then we'll inspect it first. So we can just schedule that way. So these variables are the things that they put into the model. So again, there's a ton of processing and a ton of just data exploration that happened before this. There were many more variables before. They cut them down to this, and then even here they fit the like kind of a lasso-y type thing where it still selected some of the variables out. So it threw some of the things out. So some of the important things were, so this is, I think, groups of inspectors are labeled by color. I forget exactly how they do this, but essentially there's each restaurant has an inspector, and they're labeled blue, brown, green. So this is just for privacy of the inspectors. And so there's some indicators here. So if they've had past critical violations, if they've had any past serious violations, which is a different kind of violation, I guess. And so there's a bunch of things that might be predictive, and we actually find out are quite predictive of whether or not this establishment is going to have a violation. And so I want to talk a bit about the model that they actually used. So we talked about logistic regression, and we even used ridge regression in the last homework. But I wanted to show you guys exactly what logistic regression was doing again, just to refresh the memory and to introduce ElasticNet. So Lasso, what it does is it takes the model fit and then it penalizes by this L1 norm. And essentially what it does is it forces the betas that are selected through the model to be smaller. And Lasso has this really nice property that it asks for them to not just be small, but it actually shrinks some of them to 0. What that means is that they no longer play a role in prediction. And what that means is that for you is that you can throw them away. So if you have a ton of variables, you can select the variables using Lasso in that way. And so ridge regression, I'm not sure if we actually got into the details of it, but ridge regression essentially does the exact same thing, except that it penalizes by the L2 norm. So it just takes the squared length of parameter vector beta. And so what that does is it doesn't have the nice property that it shrinks things to 0, but it does have the nice property that it shrinks things, and it improves prediction, things like that. So this is actually related to, if you're interested, to the empirical Bayes thing we're going to do in this homework, in that essentially the empirical Bayes is a ridge regression with the normal pi, which is what we give you in the homework. So why am I talking about this again? So the reason I want to talk about it is because in their model they use this elastic net regularized logistic regression. So they essentially do the exact same thing, except that they penalize both beta 1 and like the first norm and the second norm of beta. And what this does is this ensures that you have that shrinkage property where you start throwing variables out, and this one shrinks things nicely for prediction. And so it has both elements of both ridge regression and lasso. So it's a really interesting method, and it yields some pretty nice results. So one thing though is that, at least just for you guys in your project, is that they didn't really justify the use of this model. Like, why didn't they just use lasso, or why didn't they just use? I realize that they want to improve prediction, so they do regularization. But anyway, there wasn't enough details in their write-ups about this, and that's something that if you actually go and read the read the write-up, you'll notice that too, and that's something we want to sort of have you guys improve on. I explain why you're using a particular model and why not use some other alternatives, things like that. So just important to keep in mind when you actually go read this the project later on. Okay, so ElasticNet is fit just like Lasso. We've used Lasso logistic regression before, and so here I fit it. So there's this thing called Lasso Path, which I don't think we've seen before, because normally we try a lot of different regularization parameters, alpha, which are up here. So how we've done it in the past is we've tried a bunch of different ones and then selected the best one, right, using cross-validation. But I wanted to show you guys something slightly different. I wanted to show you what these parameters look like for a wide range of regularization, because this is generally what people look at, and they talk about things like importance of variables and prediction and things like that. So I want to talk a bit about that. So after I run both Lasso and ElasticNet, here are the paths. So here's the ElasticNet path, is the dashed lines, and the Lasso path are the solid lines. So this is minus log alpha. So small values of this is a large amount of regularization, so it's a little backwards. But people like looking at this because it spreads things out a bit and it makes things nicer to look at. So over here, for small values of this is a large alpha. All the betas are essentially 0. So what this means is that as I move from left to right, different variables are going to start coming in. So for example, here, the ElasticNet lets in variables first. And which variables does it let in? Well, I'll talk about that in a bit. But what I want you to sort of gauge is, ElasticNet and Lasso are doing very similar things. Their paths are very similar, meaning that the size of the betas as I add more or add more regularization are pretty much the same. So this is something that if you end up using Lasso or ElasticNet for that matter, it's really important to look at these paths, but it's more important to do some form of validation to choose your level alpha, which is what we've sort of talked about in the past. I just want to show you something different. Okay, so then what I did was I concentrated on the ElasticNet paths because I actually wanted to talk about the variables that are predictive. So again, this is the coefficients. These are the coefficients, And what this is saying is that, so the colors are a bit off, but I'll point you to this one. So first off, what I did was, these are all the variables. There were a total of 16, I think, or did I think no, yeah, they're all here. All the variables are here, and so I'll remove some of them just to make things a bit easier to look at. Okay, so these are the 5 largest, so largest in terms of this value here. So there was a bunch here that were kind of really, really small. So I want to get rid of them for a second. What this says is that as I add more and more regularization in this way, the most important variables are the inspector blue and the inspector purple. So the actual inspectors make a huge, huge difference. And that's really important for people to know. But some of the other variables that are super interesting are that the past critical violation, of course, is going to be indicative of whether or not they're going to have a violation again. And and then the consumption of premises incidental activity. So this is I had to look it up, but it's a license for serving alcohol. So it's also predictive of whether or not they're going to have a violation. Bars are dirtier, I guess. I don't know. Okay, so I write a bit about reading these path charts here. And so, again, like I talked about earlier, the really, really impressive thing about this project is how they did their validation. So essentially what they did was they took data before July 31st. So just for reference, they did this around August of 2014. So this project was running for a while. And so they decided to, starting September 1st, they were going to do a test. So that's why they actually did this. So, but they actually, everything took a little bit longer than they thought. So they actually did, they just blinded themselves to these outcomes, used only this data to build and to tune the parameters. And then they started from September 1st to October 31st, they did the test, and I'll talk a bit about how they did that. Okay, so again, they used the data before July 31st, 2014, so that's all the data starting from 2010 to 2014. They used that to fit the model. Then they used August 1st through 31st as the what we've called the validation data set. So they used this to tune the parameters, and so they did do the parameter tuning and all of this, but they only used this validation data set. And the reason, actually, so they couldn't do cross-validation because it doesn't really make much sense. Everything is running linearly through time. So you're going to use data up until July 31st to predict what happens next month. So it doesn't make sense to actually, you do a cross-validation thing between these two. So that's the reason they did that. And that's very in tune, again, with what the goals of the project were, is you're going to use all the current data that you have to predict what's going to happen later. And then, so they did that in their train validation steps. So it's really important to keep in mind exactly how you might use the model, especially when you're writing these things up. Okay, so, and then so then now it's August 31st. There are a total of 1,600 food establishments that were scheduled from September 1st to October 31st. And they basically just let them go on about their business. And they said, okay, well, you guys go on and inspect, and if you find critical violations, just let us know. And what they did was then they said, okay, well, what if we had scheduled their visits instead of just letting them do their visits? Okay, so if we had scheduled their visits, we would have sent them to the most critical places first, and they might have discovered those critical violations first. And so so after this 2-month test period, what they did was they compared what their schedule, or what would have happened if they followed their schedule based on the model, meaning the probably most critical place is inspected first, and then you keep going down the list. So basically, you put off the ones that you don't think are going to have critical violations to the end, instead of mixing them up the way that they might when they go out about their business normally. And what they found was that so here's 0, and they colored them differently, so that basically they're trying to point you to the fact that using their schedule on the most critical violations, go to them first, they would have found these critical violations, up to 60 days earlier. So this is, again, over 2 months. So there was at least 5 places that they checked last that they should have checked first, in a sense, or earlier, at least. But the important thing is that the average of this histogram is 7.1. So on average, they were able to get to the places 7 days earlier. And of course, you are going to suffer a bit. You didn't think were going to have critical violations, but it turns out that they did. And so you would have scheduled them a bit later. And so if that's unclear, this is actually this is my second favorite plot. I'll show you my favorite plot later. This is the number of violations to date. So this is a cumulative number of violations for the period of. Actually, I think I got the months wrong. September to, well, whatever it is. Oh no, that's right. Okay, so and you see that the data-driven schedule would have gotten many more than the business as usual schedule, and you see that maybe this is a bit linear. This is kind of curved, so that means that you would have had more found earlier than the business as usual, and so another way to show this, which they go through, another way to show this is sort of by day, to say, okay, on September 1st, what fraction of the inspections actually had critical violations? And if we had used our data-driven schedule, we would have had, more than half of the inspections would have resulted in critical violations, which is great. And while business as usual is sort of 15 or something %. And of course, you're going to run out of violations much more quickly if you're discovering them all earlier, but that's great, right? So it prevents diseases from spreading and things like that. So so I thought this was another great way to show it. This is a smooth version, of course, because this is just a fraction. On September 1st, there's just a number here, and on September 2nd, there's just a number. So this is a smooth version. They use looks like a Gaussian process smoother, but it's unnecessary in a way, but it looks much nicer. See here they have smooth results. And then the last thing I want to show is this plot. So this is just sort of saying, putting things in the scope of the best and worst, best possible situation, the worst possible situation. The best possible situation is that all of the critical violations get inspected. They're at the top of the list. And so you're going to run out of them pretty quickly. So in the first maybe 10 or so days, they discover all the possible violations. And then the yellow is the worst possible case, meaning that you don't check any of the food establishments that had critical violations until the end. And it sort of just puts things in perspective, and it looks nice. But anyway, so that's sort of all the results that I want to talk about. And so there's a few notes that I want to kind of leave you with. In terms of the projects, this is a great project in terms of how they present their results. Obviously, they don't have everything that we ask you guys for, but I thought it was a great project anyway. And so one of the most important things is that because of the way that the problem is set up, it makes sense to validate things in this way. And that's something that, when you're thinking about your project, do think about how you might use the model that you build and what it would mean. Because you guys all have really interesting data, as I've seen so far from the proposals. And so do think about that, because it's a really important part, especially when you're trying to communicate the results to people who don't know what a elastic net is. So, okay, that's all. That's all for this week. Thanks.